Hello guys, welcome once again. My name is Richard. So today we're going to go through quantum numbers and our way to electronic configuration and figure out how they all came to be. So a little bit of background history. After Heisenberg came and then said that you cannot find the position and then the momentum of an electron at the same time, the theoretical physicist or the scientists at that time decided to come up with a way to figure out how to find an electron. So they came out with a system of probabilities, and then they came out with four numbers. So those numbers are called the quantum numbers, and we're going to go through them today, and so that we can get an end to the chapter one of the quantum mechanical model of the atom and the chapter one of the chemistry book, so that we can be done with it and we can move to chapter two. So, but before we go into it, there are some things that I want to clarify over here. There are some keywords that I've written on this side of the board that I want to clarify before we jump into it. So I'm gonna move here real quick. The keywords that I want to clarify is number one is energy state. So when we talk about energy state, we don't mean potential energy or kinetic energy in the sense of quantum mechanics, because what in the MCAT is testing it so that you do not confuse it for potential energy or kinetic energy. Energy state, right, is the description given to an electron by the quantum numbers. Energy state is the description given to an electron by the quantum numbers. So the series of quantum numbers that you write for a specific electron is that electron's energy state. I believe we've gotten that notified. And then also we go to shells. Now people would confuse shells for orbitals. They are two different things. Shells are the main energy levels. They are the main energy levels, like the main clouds around the nucleus of an atom where an electron can exist. So shells right here, once again, they are the main energy levels that an electron can exist in. So inside the shells, that we could divide the energy levels into different subunits. But then the shells are the main energy levels. The subshells over here. Now the subshells are a step below the shells. So we take the shells, we divide the shells into the subshells. So they are the energy level, or they are the energy level below the shells, not the main energy level, but they come below the shell. So if you are arranging them from biggest to smallest, this would come first, and then subshells will come second. The name should even give it off. And we go to orbitals. Now, orbitals are sub of these subshells. When you take the orbitals and you divide those orbitals into some particular energy states or energy levels in those subshells, then you get orbitals. So you'll get this once you move on. Take p orbital, for instance, right? If we take p orbital, for instance, the main energy level could be that the shell could be like, let's say the n equals to 2 shell. If the n equals to 2 shell, the subshell, which is a p, would be the subshell 1, L equals to 1. And then the orbital, so the L equals to 1 gives us the p subshell. And then the orbital, which is ML, right? Let's say the ML negative 1 would give us the orbital here. So in this case, the X. So that is why when we write like the p orbital, we have px, py, and then pz. The p here, over here, they are the subshells, and the x one over here are the orbitals. So these are the subshells, and then these are the orbitals, right? But if you talk about the shell, which is the main energy level, it could be n equals to 2, right? So all of this could exist in one shell, if you get what I mean. And then let's move on to suborbital. Suborbital is not a real word. It doesn't exist in quantum mechanics. People confuse it with subshells, but it is not a real word. So get suborbital from your mind. It doesn't exist. suborbitals do not exist in a quantum sense. Okay, so we're gonna erase it from here. And the probability density. When we talk about probability density of an electron, right, it is the chances of finding an electron in a space or in a region, right? So that is the probability density, is the chance or the probability of finding an electron in a specific region that you have found. So if we give you the probability density of a specific region, that is the probability by which if we go to that region, we're going to find an electron. So those are the things that I wanted to clarify before we move on to the main aspect for today. So I will get rid of this real quick. Now, because you cannot find the momentum and then the position of an electron at the same time, scientists came out with the quantum numbers. They came out with 4 distinct quantum numbers. The first one that they came out with is the principal quantum number. Now, I want to talk about the principal quantum number. We mean the shell. It is the main energy level of the atom. So that is the main energy level. So the first thing that came to you about like shell n equals to 1, n equals to 2, like the same thing that Bohr uses to represent his hydrogen atoms. Those same energy levels, they are the principal quantum numbers, right? They are the main energy level, right? So they are the main energy level of an atom. So once that we found the principal quantum number 1, and then they can take any integer, any positive integer, can take the value of any positive integer. So they can take the value of any positive integer. So they are demarcated by n. They take the value of any positive integer. So from 1 all the way, from 0 all the way, from 0, 1, 2, 3, all the way to infinity is the principal quantum number. Now, because they are the main energy levels of the atom, they take any positive integer, but then there are an amount of electrons that can fit into the principal quantum numbers. There are the maximum amount of electrons. So the maximum amount of electrons, so max electrons that can fit into the main energy cell of an atom is given by this equation 2n squared. Now we can go ahead and try to prove this to equation, but it is interwoven with the other quantum numbers. So for me, what I would suggest is try to memorize this into your head. If you're gonna come up with a mnemonic to get it, right? So the 2n squared is the maximum amount of electrons that it can take. Now, also, one thing that you should note is that when we talk about the principal quantum numbers, right, the further you move away from the nucleus of an atom, the lesser the energy, or the lesser the main energy would be. So the lesser the energy that a principal quantum number would hold would be. So, for instance, and then, so for instance, remember when we was doing the amount of energy that an electron can have exhibit on an atom, we use like the Rydberg unit of energy equation to find it. This equation RH, or divided by the n square over here. We use this equation to find it. So the one way that you could use to prove that the energy as you move away from the nucleus. So the only way that you could know, or you could try to remember, principal quantum numbers works as gravitational energy. The further you move away from the nucleus, the lesser it gets. So that is the principal quantum number for you, demarcated by letter N. And then the maximum is this. So these are the two main important things you need to remember about the principal quantum number. So it is the main energy level, and they take on any positive integer. But the most important thing is this: the maximum amount of electrons that it can hold is 2n raised to the power 2. So now let's get our mind away from the principal quantum number. And then secondly, let me switch markers. So number 2, we have the azimuthal. Is it TH or T? I think it's TH. Azimuthal quantum number. And that is demarcated by the letter L. Now it is demarcated by the letter L because this azimuthal quantum number is the same as the angular momentum of the electron, right? And angular momentums are represented by L. So that is why we could also represent this one by L. Now with this azimuthal quantum number, right, it depends on the principal quantum number. The principal quantum number define this azimuthal quantum number. But what this azimuthal quantum number do is also describes the shape and the number of subshells, like the number of possible subshells. So the principal quantum number gives the shells. The azimuthal quantum number gives the number of subshells and the shape of the orbital or of the energy state that the electron occupy, or the cloud, or the probability density that the electron occupies in, right? So those are the principal, the azimuthal quantum number. So the azimuthal quantum number is given by any integer, so it is any integer from 0, right, to the principal quantum number, which is n minus 1, right? So in that sense, this will not be just a single number, right? It will be a set of numbers. For example, if we have a principal quantum number of 3, our azimuthal quantum number would be n minus 1, which is going to be 2, right? And then from 0 to 2, we're going to have 0, 1, and then 2. So there we have 3 possible number of subshells. Got it? The azimuthal quantum number would be a set, and then these sets would give you the possible number of subshells that the electron would exist in. So it could be subshell 0, subshell 1, subshell 2, right? Another example, if we have the principal quantum number, right, n, gives us, let's say, if we have the principal quantum number n equals to, say, 4, then our azimuthal quantum number would be anywhere from 0 to n minus 1. So the azimuthal L will be 0 to n, which is 4 minus 1. So then it's going to be 0 to this 2 to 3, right? And there so from that point we get 0, 1, 2, 3. So that is how you get it. But there is something that I really also want you to put in mind so that it will be like an easy points to score on the MCAT. So let's say I have a series of, so any integer from 0 to n minus 1. So on the MCAT, let's say I have a series of azimuthal quantum numbers, that being like 0, 1, 2, 3, right, all the way going, right? So let's just end it at 3. This zero number here, right, it represents the s orbital, right? This 0 represents the s orbital. This represents the p orbital, so p orbital. This represents the d orbital, and then this represents the f orbital, right? So the 0, s orbital, p orbital, d orbital, f orbital, right? I'm assuming that there are some more orbitals of some specific shells, but then we're not going to go all the way over there. That is quantum stuff. But for the scope of the MCAT, this is something that you should know. And something that, the thing that I used to remember this is when I was a kid, I used to watch this Power Rangers. It was called SPD. So I remember them, SPD, right? Emergency. And then when they are fighting, there is always like a fire or fighting. So SPDF orbitals. You get a point. This S is the 0. Is the 0. This is the 1. This is the 2. And this is the 3. So that is also all about the azimuthal quantum number that you seriously need to know for the MCAT. And there could also be a periodic table diagram, like an eye memorization part of it that you could also put in your head, or just put it in the back of your pocket just in case. So if you take the periodic table, right? If you take the periodic table like this, right, and then you go all the way like this for the transition metals, and then we go over here for the halogens, and then the noble gases, and then the semi-metals, and we put the lanthanines and then the actinides down here. So if you take the periodic table, there are 7 division. We will do periodic table, that is the next chapter, but for now this is 1, say 2, say 3, say 4, say 5, say 6, and then 7. It goes on like this all the way like that. So if you take the periodic table like this, and this is just both lanthanines and then actinides. This part, right, this part is the S block. This part is not O block in Compton. It is S block in quantum chemistry. So this part is called the S block, my SGs. Oh, my SGs. And to the far right is the P block. Now, P block. P blocky. And in the middle here, so all these parts, like all this, all of these. So talking about the alkaline earth metals and then the alkali metals, they are all the S block. And when you come here, all of this is the P block dudes right here. So all your halogens, your semi-metals, your noble gases, they are all also in the P block. Now in the middle here, those that want to be in the middle, pause. In the middle here is the D block, right? And then down here the notorious lanthanines and the actinides are nothing but the F block, right? So in the middle is the all over here. So all your transition metals, they are your D block dudes. So that is a way to arrange or have a visual representation of it, because if a question like that pops from the chemistry part of the MCAT session, maybe a discrete question asking you which orbital, like some electron in some elements, would fall in or would exist in, you could just picture if the element is like falls here, if it's falls here, if it's fall here, or if it's down here, then you will know that it will go into an F block, D block, P block, or an S block, right? So for that, they also saying there is another thing about the azimuthal quantum numbers, that is the maximum amount of electrons that the subshells can carry. So these are the azimuthal quantum numbers are the subshells, and then the maximum number of electrons they can carry. So max for the subshells equals to 4L plus 2. So I'm going to straight here and put the formulas that we do learn over here. 2n squared. Now we are at 4L plus 2. We will come to all these to refresh our brains on it. Once again, we're not going to go over how to prove the 4L plus 2, but rather memorize it. It would help a lot if you know the maximum number of electrons that these subshells can hold. 4L plus 2. So if you are given the L number, or if you deduce the L number, then you just put it in there and then figure out how many electrons would go into that subshell. So from the azimuthal quantum number, so once again, what did we learn from the azimuthal quantum number? What did we say that they are? So one is they represent the subshells, right? They represent the subshells, right? And then also two, they take any value from 0 to n minus 1, the principal quantum number minus 1. And then three, the maximum number of electrons they can hold is over here, right? And maybe you could say that they are demarcated by L. But those are the main points that you need to take off from the azimuthal quantum numbers. From there, we go to our infamous magnetic quantum numbers. So the magnetic quantum numbers. What the magnetic quantum numbers represents are the orbitals. So have you seen how they go? The shells are the principal quantum numbers, the subshells are the azimuthal quantum numbers, the orbitals are the magnetic quantum numbers, right? So if these are the shells, then they represent like which shell that the electron is likely to be found on, like which orbitals, excuse me, it's not shell, it's orbital. So they represent which orbital electrons are likely to be found in at a moment in time. So yes, it has to be at a moment in time, because electrons are constantly moving and they do not stay in one orbital like how we would classically think they are. They jump from orbital to orbital everywhere. They are like the toddler, like the most energetic toddler playing around in your house. They would move everywhere, jump everywhere, be everywhere. They want to see everything, right? So that is how electrons usually behave in an atom. But these represents the orbitals. And then also, if they represent the orbitals, they take on the value. So they take on the value from the negative integer to the positive integer of the principal um of the azimuthal quantum number. So what I'm saying is that they take the value of the azimuthal quantum number is demarcated by L of negative L, right, to positive L. So for instance, if we have an L number of 2, if we have an L number of 2, so if L equals to 2, the magnetic quantum number would be, it's also like it's a series of numbers, like a set. It will be from the negative to the positive, like if you are on a number line. So it's going to be -2, -1, 0, 1, 2. So 0 is included in it. And then these numbers, how many they are, represents the orbitals that they are. So in this case, it's 1, 2, 3, 4, 5. It's 5 orbitals. So then it would be the D subshell. And then the D subshell can be found in, let's say, the N equals to 3, or the N equals to, if this is 2, then it can be found in the N equals to 3 principal quantum number shell. Right, I'll make a visual representation of it so that you will get it. So these are the magnetic quantum number. 1, they represent the orbitals. 2, they take on the form of -L to L. And then the maximum number, so all of them. So the maximum number of electron that goes in an orbital, right? The maximum number of electron in an orbital is 2L plus 1, right? So let's go here and then also put this formula down here so that we don't lose track of it. Two L plus 1. So this is all about the magnetic quantum numbers. So what are they? They represent the orbitals. They take on the value of the azimuthal quantum number, -L to L, and then the maximum number that it could take is 2L plus 1. And we are also not going to go through this to figure out or to, prove that the equation is right. We just have to commit them into memory. And they follow a specific pattern that we will get into that later on. So that is all about the magnetic quantum numbers that I want to say. But then there is something that the MCAT also really tests, like the shapes of orbitals. Usually it tests for the shape of s orbitals and p orbitals. As you descend into d and f orbitals, the shape becomes geometrically complex because electrons, the orbitals that they exist in, occupy a 3D space. So it's going to be hard to represent a three-dimensional object on the 2-dimensional board right here. But let's say I have this, right? This is this 3D box right here. This 3D box right here is an orbital, right? Is the P. Let's say it is the P subshell. The P subshell. Now the P subshell has 3 orbitals: the px, the py, and then the pz. It goes on all the 3 dimensions, all the 3 planes of this thing. So the first plane is, our top to bottom. So our top to bottom would be like, and it takes the shape of a dumbbell. So like that, it will be like this, right? And then the next one would be our bottom to like our left to right. So that would also be something like on this axis, right? And then the third one will be like a diagonal, like making it looks like it's a third dimension, right? So something like this, like let's say this shape, something like this shape. So this one is px, uh, py, and then pz. It goes on like these dimensions. So another way to also visualize it is drawing, let's say, a regular two-dimensional Cartesian plane, but then demarcating another dimension for z. So if this is my y, x, and then z, they go like one, the py, another one like this would be the px, and then on this plane, the z plane over here, once again the shape of a dumbbell will be the pz, right? You see how it goes? This is a little bit kind of weird, trying to represent a 3D thing on the 2D surface, but that is how you would visually represent it on the board. So that is all about the magnetic quantum numbers. So let's move on to the last quantum number. So the last quantum number is called spin quantum number. Spin for a spin quantum number. Now, the spin quantum number does not necessarily depend on the principal, the azimuthal, or the magnetic. It does not depend on any of them. The spin is how the electron is rotating in the orbital. So it's either rotating clockwise, spin up, or counterclockwise, spin down. That is it, right? Or it's either rotating clockwise, spin up, a positive half, or counterclockwise, spin down, negative half. That's it. So the spin quantum number is either spin up, which some case is demarcated by an up arrow, or negative or positive half. So it could be equal to this, equal to that, or spin down, which is also like a down arrow, something like this. So it's the arrow. If you're supposed to extend it, then it will be an arrow. So this case is like half an arrow, like that, and it's also equals to negative half, right? So in this, like, let's say in this subshell, if you have like an electron in it, it would, let's say, exist here, a spin, a spin, a spin, a spin, a spin, a spin, right? Then we can have like another spin, 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 another spin, another spin, and another spin. It could be like that. So there isn't much about the spin quantum numbers, but that is what you should remember. Now let's summarize everything we've learned about the quantum numbers, and then make hay while the sun is shining. So we have principal quantum number, principal quantum number, azimuthal quantum number, magnetic quantum number, and then last but not the least, spin. quantum number. So when you have it like this, the principal quantum number dictates for the azimuthal quantum number. Without a principal quantum number, there is no azimuthal quantum number. And what did we say the principal quantum number was? It was the shell, right? The shell. And what are the shell? They are the main energy levels, right? So main energy level is that. And is demarcated by the letter N, like that. The second one is the azimuthal quantum number. So this has to dictate for this, right? Inside the principal, we get the azimuthal. The azimuthal quantum number is represented by L, because we also said that it is the same as the angular momentum, and that is an L. So, and what did we say that was? That was equal to the sub shells, right? And when we say they are the sub shells, what did we say they equals to? What did we say the maximum number that they can hold? So the maximum number that they can hold is 4L plus 2. We did not do the maximum number the quantum number can hold. Quantum number, the maximum is 2n squared. Like that. And we move on to the magnetic quantum number that is also demarcated by M subscript L, magnetic quantum number or magnetic angular momentum, which is equals to, what did they say they are? They are the orbitals, right? And what is the maximum number of electrons an orbital can hold? They can hold 2L plus 1, right? So they can hold 2L plus 1. And then we go to the spin quantum number. For that, what did we say they are? Spin up, which is an up arrow, or spin down, which is a down arrow. And the spin up can also be written as half, and the spin down is negative half. For the principal quantum number, we said this is the subshell, is the shell. This is the maximum number it can hold, is the main energy level of the atom. The azimuthal quantum number depends on the subshells, and then it takes anywhere from 0 to, into bracket, n minus 1. That is how it takes. The azimuthal quantum number dictates for the magnetic quantum number, right? And that is our orbitals, and the maximum number is this. So let me just, write the maximum number in front of them. So this is max. And how do we derive this? It's also, we derive it from this number. So that would give us something like this. It's also from 0. No, that is like the L, right? So it is from negative L to positive L. And after that, we come down to the quantum, the spin quantum number. So one more time, let's go over this. The principal quantum number is the shell. They are the shell numbers, and is the main energy level of the of the atom. And the maximum number of electrons it can hold is 2n squared, where n is the principal quantum number. The azimuthal quantum number is demarcated by L. L because it is also an angular momentum quantum number, right? And it is the subshells of the shells. And it is derived from, that is why this arrow is there, it is derived from the principal quantum number. How is it derived? We take the quantum number and then subtract 1 from it. So when we subtract 1 from it, then we count from 0 to the number we get. So that's why we have 0 to n minus 1 over here. Now, from the azimuthal quantum number, the magnetic quantum number is born. It is demarcated by ML. L because of the angular momentum quantum number over here. And what are those? Those are the orbitals. And how do we derive them? They are derived from this, right? We just take their value and then we count from its negative counterpart till we get to that value with 0 included. So from 0 and from negative L to positive L. And what is the maximum number that it can hold? 2L plus 1. Then last but not the least, we have the spin quantum number, which is just 2. It does not depend on any of these, right? So we either spin up or we spin down. And then we spinning up is demarcated by half. We spinning down is negative half. So that is all for the quantum numbers. So our next topic of discussion is electron configuration. All right, guys, thank you very much for watching this video. I appreciate all the support. We will continue the electron configuration in the next video. Right now, I have to go to work. Please like, share, and subscribe. Thank you.